3.4, 3.5, Part 1. The zeros of polynomial functions. A polynomial function of degree n takes the form p of x equal a sub n times x to the nth power plus a sub n minus 1 times x minus x to the n minus 1 power. And this pattern continues until we get our linear term, a sub 1, x to the first, and then just our a sub 0, our constant term, where all a sub I are complex numbers, and a sub n can't equal 0, and n is a whole number. So all of our degrees are whole numbers, and our first leading coefficient can't be 0 because then it would take away degree n. Recall that a complex number looks like a plus or minus bi, where a and b are real numbers, and I is the square root of -1. I is the complex part of that number. So note that if a complex number is real rather than imaginary, b would be 0. So the imaginary part would go away, and then it would be a real number. But if you have a and b and I, this completes our complex number. So we're going to be doing some linear factorization. So basically what that means is that we take polynomial p of x, and it has exactly n linear factors such that they can all be written as linear factors. Notice how linear is part of this. So each of their degrees is going to be 1. Each of the factors of a polynomial has a corresponding 0 or root, an x value that causes the factor to equal 0. If the 0 or root is real, it will appear in the graph of the polynomial as an x-intercept. So, zeros of multiplicity. If x minus c occurs as a factor of a polynomial m times, then c is a zero of multiplicity m. We've talked about this before, so here's another example. If I have two factors after I factored p of x, and they are exactly the same, then this means I can write them as having a multiplicity, which is more than 1. So our x minus 2 has a multiplicity of 2, and our 2x plus 1 has a multiplicity of 1. Now, there are many ways to factor a polynomial in standard form, so let's begin with that. The first method is factoring using the greatest common factor, the GCF. So we're going to factor number 1 using this concept, and then the graph actually to the right is also corresponds to number 1, so we're going to match up what we get and compare it to what we have. Okay, so my GCF for all three of these terms is going to be x squared. So that means I can take out an x squared, which is essentially dividing each of those terms by x squared. So we're left with 2x squared minus x minus 1. And that's set equal to 0. So we need to factor using decomposition, or factor by grouping, essentially. So we have a times c, which is -2, and then what multiplies to give you -2 that adds to give you -1, that middle term? Well, that's going to be -2 and +1. So we're going to separate that middle term, and instead of writing minus x, we're going to write minus 2x and plus 1x, and then that minus 1 comes along. So the reason why we do this is now we can group them because we have an even number of terms. And then our next step is to take the GCF out again. So, this should be x squared in front. So x squared is still tagging along, but now we're going to pull out a 2x in that first binomial, and we're left with x minus 1. And then we're actually not going to pull anything out, so essentially it's a 1, and we're left with x minus 1. So because these two are the same, then we can say that's one of our factors. And then what you do is you take the GCFs that we pulled out and put them together to formulate your other factor. And then that x squared comes down because that's a factor as well. So it's good to notice that we have a degree of 4, so we should have 4 zeros or 4 solutions, and we do. So the zero product principle says that each of these, if we set equal to 0, we can solve. So we're going to do that. And when we do that, we get the following zeros. We get x equals 0, x equals positive 1, and we get x equals negative 1/2. Now, we also need to note the multiplicities on each of these. So, to get 0, I had x squared, which means this has a multiplicity of 2. This factor had a multiplicity of 1, and so did negative 1/2. So if we compare it above, then we have, it's kind of pixelated, but we have it going through 0, 0, going through 1, and then negative 1/2. And what's important to note, though, is that it comes down, it goes a little bit under, and it actually bounces. Again, it's hard to see since it's pixelated, but it bounces at 0 because we know that it has a multiplicity of 2, and that's what a multiplicity of 2 looks like at that specific 0. Okay, the next problem, GCF. The first thing I'm going to do is take out an x. And I'm left with x squared minus 2x plus 1. So I can factor this. What multiplies to give you 1 that adds to give you negative 2? Positive 1. It shouldn't be negative 2. I'm sorry, it should be positive 2. So what multiplies to give you 1 that adds to give you 2? 1 and 1. So we have x plus 1, and we have x plus 1. Now we can rewrite this, and it's important that we do so we can see that multiplicity, that x plus 1 is going to have a multiplicity of 2. So the zero product property states that we can set each of these equal to 0, and we have x equals 0 and x plus 1 equal to 0. So therefore we have x equals 0, which is pretty obvious, and we have x equal to negative 1. So x0 had a degree of 1, so it has a multiplicity of 1, and x plus 1 had a degree of 2, so it has a multiplicity of 2. So let's review multiplicity really quickly. If we have a multiplicity of 1, it goes straight through that x value, so it can be one or the other. If it has an even multiplicity, it's going to come down and hit the x-axis and go back up and bounce, if you will. And it can do that above or below the x-axis. And then if it has one that's greater than 1 and m is odd, it's going to kind of curve through that point and almost look like it has a cubic behavior, but it's not going to go straight through. It's going to curve through like this. Okay, so factor by grouping. Well, we did this essentially in number 1 above because we had to write a trinomial as a polynomial of 4 terms, which allows us to group. So now, instead of rearranging it to factor by grouping, if we're given a factor or a polynomial that has 4 terms, that's, if there's no GCF to take out, that's something that you definitely want to look at first. So, just like before, we start by breaking it up into 2 groups. But remember, you have to have a negative or a positive in between, so we need to do plus a negative 4x there, so we group correctly. So the GCF in my first one is x squared, and I'm left with x plus 5. And in the second one, I'm going to take out a negative 4, and I know I want to take out a negative because I want this negative in the middle here to become a positive, which it does, so now it matches my other binomial. So we have a factor of x plus 5, and then the GCFs together give me x squared minus 4. So it's important to know how to factor because we have to factor this again. So x squared minus 4 is the difference of two squares. So in linear factorization, we have x plus 5, x plus 2, and x minus 2. So the zero product property tells us that we have x values at negative 5, negative 2, and at positive 2. And they all actually have a multiplicity of 1. Number 4 is a little bit different. It needs to be set equal to 0, just like you've always known when you factor. So I'm going to get x to the third minus 3x squared minus 4x minus 12. So now we can factor by grouping. So I'm going to group the first two terms. I'm going to make this plus a negative, so I group that correctly. The GCF of my first one is x squared. The GCF of my second one is negative 4. Oh, I made a mistake. This should be plus 12 because I had to add it to the other side, which now makes sense because now I have x minus 3 as I should, and these two match, so that's one of our factors. And then again we have x squared minus 4, so we actually have to go one more step further and solve the difference of two squares. X plus 2 and x minus 2. So the zero product property says that we have zeros at x equals 3, x equals negative 2, x equals positive 2. And again, they all have a multiplicity of 1 because each of these linear factorizations have a degree of 1. Now we're going to factor by variable substitution. So since this is a quartic function, we can't really factor it unless we just say, let u equal x squared. So I'm going to go through and I'm going to replace. So that means that x to the fourth would then be u squared, and then x squared would just be u, and then 24 would be 24. Well, now that we did this, we can factor it. What multiplies to give you 24, that adds to give you negative 10. Well, that would be negative 6 and negative 4. So if I solve this using the zero product property, I would have u equal to 6 and u equal to 4. But now, since we solved, we need to go back and replace u with x squared, which would be x squared equals 6 and x squared equals 4. So now we would solve by taking the square root of both sides, and we would have x equal to plus or minus root 6 and x equal to plus or minus 2. So this gives us 4 solutions, 4 roots, 4 zeros, which makes sense because we have a polynomial or a trinomial of degree 4. So if I wanted this in factored form, I could say, well, knowing that I have a 0 as x equals positive root 6, I would say x minus root 6, x plus root 6, and then I would have x minus 2 and x plus 2 in factored form. So those zeros are root 6, negative root 6, 2, and negative 2. And again, they all have a multiplicity of 1. if you look at the graph, you see that we have those 4 zeros just like we just saw for. All right, in 6, let u equal x squared. So we have 2x squared minus u minus 3. So I'm going to have to factor by grouping, which is decomposition. So I get -6. What multiplies to give me -6 that adds to give me -1? That would be -3 and 2. So I would write 2. Oh, this is supposed to be a u, not an x. Sorry about that. Okay, so I'd have 2u squared minus 3u plus 2u minus 3. And again, we're going to factor by grouping. Group the first two, group the second, pull out a GCF of u, and I'm left with 2u minus 3, and then 1 over here because I have 2u minus 3 already. So I would have u plus 1 equal, u plus 1 and 2u minus 3. Well, this would mean u equals to -1 and u equals to positive 3 over 2. And now we're going to switch back because u equals x squared. So x squared equals to -1 and x squared equals to 3 over 2. So if we did the square root of both sides, we would have the following zeros as x equals, well, square root of -1 is I, so I'd have plus or minus I, and over here I'd have x equals plus or minus 3 over 2. Again, in factored form, that would be x minus I, x plus I, and then we'd have x, sorry, I'm all over the place tonight, x minus root 3 halves and x plus root 3 halves. So we have zeros at x equals I, x equals -I, x equals root 3 halves, and x equals negative root of 3 halves. And all of these have a multiplicity of 1. So if you get a complex answer, don't worry, that's definitely possible. So remember that a polynomial function of degree n has exactly n factors, but the zeros aren't always real like I just said. Only the real ones would appear as x-intercepts on the graph though. So if you're wondering, I have 4, why don't I physically see on the graph 4 zeros? That's why, because 2 of those are going to be complex. All right, so we can use the graphing calculator, but this should only be used as a last resort and only if all methods fail. So please make note of that. So what would that look like? Well, what we do is we need to, when we use synthetic division, what happened is all other factoring methods failed. So we need to graph. We're going to find one and only one zero, and then we're going to do synthetic division. So if I were to put number 8 in my calculator, and I do second trace and I calculate the 0, then from this, so from the calculator, I got that there is a 0 at -2, which means I have a factor of x plus 2. Well, if it's a 0, it goes in evenly, which means I can divide it out. So if I divide it out, hopefully I'll get a quadratic that I can factor. So up here in my dividend, I'm going to have coefficients of 1, -4, -7, and 10. Since I know my factor is x plus 2, I'm going to use a -2 on the outside. I drop the 1, multiply it by -2. I add. Multiply it by -2. I add. multiply it by -2. And since I said it was a factor, you must get 0 there or else it is not a factor and you probably didn't find it correctly in your calculator. So, from doing synthetic division, I now have a quadratic, x squared minus 6x plus 5, that I can factor. So, if this was set equal to 0, we would have x minus 5 and x minus 1. So that means that my original function, f of x, can be written as x minus 5 times x minus 1, and don't forget that x plus 2. So this is the linear factorization of that original function f of x in standard form. So if I ask for the zeros, I have x equals 5, I have x equals 1, and I have x equals -2, and they all have a multiplicity equal to 1. Okay, last problem, number 9. Again, you put this in your calculator and you find 1. And there's actually only one that you can find that's going to be a direct factor of it. And that one from the calculator is going to be x plus 1. Which means that if I divide g of x by x plus 1, I'm going to hopefully get a polynomial that I can factor again. So, synthetic division, I would have 3, 2, -16, -10, and 5. And then I would have -1 on the outside because my factor is x plus 1. Again, we get a remainder of 0, which we need to do because x plus 1 is a factor. It goes in evenly. Nothing's left over. So from this, I'm going to now have a cubic function. 3x to the third minus x squared minus 15x plus 5. Well, this is a cubic function, but it has 4 terms, so we can actually factor this by grouping. So I've grouped the first two, make sure I have a plus in the middle, and now I can pull out a GCF. X squared, and I'm left with 3x minus 1, plus I take out a -5, and I'm left with 3x minus 1. So again, that original function g of x can be written as the factors x squared minus 5, 3x minus 1, and don't forget that x plus 1. Well, what does this mean? Well, the linear factorization of this, meaning we can't have this quadratic here, is if we set that equal to 0, I would add 5 and take the square root. So I would have x plus root 5, x minus root 5, 3x minus 1, and x plus 1. So now they're all linear, and I can identify my 4 zeros. So I'm going to try to squeeze this down here. I have x equals root 5, x equals negative root 5, x equals 1/3, and x equals -1. And I can't write it on there, but you can write on your paper. They all have a multiplicity of 1. So now we can take higher order polynomials and we can still answer all the questions. We can graph, but we might have to synthetically divide or factor to be able to find all the factors, our zeros, and all the multiplicities so that we can graph the function.